All right, welcome back. So in example 4 of 1-a-day 23 for Math 365, this is the system, or one version of the system. If you think about it, the problem just says the problem says we have a three-spring system attached to two masses. That sounds like it's fixed on both ends. So that's what I'm assuming here. We do have some more information. We took M1 to equal 1. M2 to equal 1, K1 to equal 1, K2 to equal 2, and K3 to equal 1 for the appropriate units, the spring constants and the masses here. So basically, the middle spring here is twice the resistance or stiffness, if you will, as the other two springs. Okay, to write the free body diagrams and the force body diagrams, I guess, of M1 here, um, you can see that the corresponding for M1 here is going to be pulling backwards and then also restoring force. So there's going to be two forces heading in that direction and then one force heading in this direction. If you imagine being pulled this way, you're gonna have kind of like two restoring forces forcing it back and one pulling it forward. So we can write Newton's second law as mx double dot, and that's the force times acceleration. And then the first force is can of course be the first spring constant times its displacement. So this one, and that's pulling it back that direction, opposite direction, to its motion from Hooke's law. Likewise, K2 here is going to also be pulling it back in the displacement value. So that's K2 X, and then our initial pull in this direction will be from also K2, but in the positive Y direction. So those are the forces that are acting upon our first mass here. And then if we consider our second mass, okay, here what we have is a similar situation, since unlike the other example where this side was not attached to another spring, so it only had two of them. This one's going to have a pulling force and then also a restoring force. And these are going to go in opposite directions because of Hooke's law. The pull is going to also be directed in a similar fashion. So it's going to have a very similar fill. So we have M2, actually this is Y, double dot, because we're talking about the motion here for this one. And this one's going to give us, you have minus um, K3 times Y. So that's the initial one here. And then if we look at the other ones, we have minus K2 times Y. That's from the spring here. And then the one going back the other direction, we're going to have plus K2 times X. Okay. All right. So those are our two equations. And now we can plug in the information that we're given and recognize here that you have a common spring factor here and a common spring factor here of the K2. So we can write this simply as minus 3x plus 2y, and this one becomes 2x minus 3y. Again, the combining coming from the fact that there are two K2s here, and there are two K2s there. So let's go ahead and take this differential equation then. And so we have, and create our system. So we have x double dot is equal to, moving these terms over, then add 3x plus 2y equals 0. And then down here we have y double dot y double dot plus 3y if I factor out a common negative, that would make adding that over, or you could think of it as subtracting. And we have plus 2x equals 0. And then realize that when we write this as in the d notation, um, this term here is going to look a little bit different because the minus sign. So this is going to equal d squared plus 3 minus 2 minus d squared plus 3 x y 0 0. I think I made a slight mistake there. Yeah, it's a plus 2y here. That should be a minus y. That's why this was a minus 2. I wrote it down, but in my head I was thinking it was a minus 2 there. So careful with your signs. I in my head subtracted it over, but I did not write it as a minus. I wrote it as a plus because I was looking at it when I wrote it. Okay. Still check all the other signs. Okay, that's good. And so you'll notice, in case you're wondering why it's in this format, I just left the 2x here and I subtracted the y double dot over and factored out the common negative. That's why it's in this form. The get reversed though when I write it in the matrix form because I'm multiplying x times 2 to get this, and then minus times this. Okay, so now it's in this form, just like we did in the other example that we just did on this one. But we need this determinant to equal 0. Okay, so we're going to go ahead and take care of that. So you get a negative d squared plus 3 and a d squared plus 3 plus 4. And if we plug in everything and multiply everything out, we get d squared plus 5 and d squared plus 1. We need that to equal 0. Okay. Which this implies that d squared is equal to minus 5 and d squared is equal to negative 1, which says that d is equal to plus or minus 5i and d is equal to plus or minus I. So what does that mean for our system of equations then? That tells us then that x of t and y of t are going to equal c1 cosine t plus c2 sine t plus c3 cosine square root of 5t plus c4 sine square root of 5t. And similarly, we'll go with a1 cosine t plus a2 sine t plus a3 cosine square root of 5t plus a4 sine square roots of 5t. Okay. So those are our two equations. And again, we don't have 8 unknowns. We only have 4 unknowns since our system has 2 equations of constants of coefficients here and 2 constants coming from each of those systems. So we should have a total of 4. So just like we did before, we can take the derivative of, let's say, x dot double dot, and we can plug it back into the original equation here. So we have x double dot plus 3x minus 2 times y. So we would plug in each of those values and set it equal to 0. Okay, and then solve and then we would do the same for each of the systems and equate coefficients once we're done. Okay, so the process is algebraically a little bit messy. However, it falls apart pretty quick, and especially if you equate. So the trick here is to equate coefficients of the corresponding trig function. If you do that, you should find pretty quickly. You're going to get A1 is equal to C1. You're going to get A2 is equal to C2. A3 is equal to minus C3. And A4 is equal to minus C4. Okay. And then we can rewrite this system as the following. So x of t then becomes C1 cosine t plus C2 sine t plus C3 cosine square root of 5t plus C4 cosine square root of 5t. And y of t is going to equal C1 cosine t plus C2 sine of t minus C3 cosine square roots of 5t minus C4 sine square roots of 5t. Okay. And so without initial conditions, we can't evaluate this beyond that. But that would be the system of equations in the general solution, a particular solution. Okay, I hope that was helpful. I'll see you in the next